Okay, so last time we were talking about Kruskal's algorithm, and remember that we were mainly discussing a problem where we had a graph and we wanted a set of edges that had the minimum cost but covered all the vertices. Right, so we looked at the Kruskal's algorithm, and essentially we said that that we would need three main components, right? The first component is makesets, that is just create individual graphs for individual vertices, and then keep on joining multiple vertices together in with respect to individual low cost edges, and we would then get multiple different disjoint trees. And once we are to connect different disjoint trees together, again with a smaller edge, we would just be combining multiple trees together. And the main idea behind combining trees was to combine them with respect to some value or some rank, such that that resulted in a tree that had the lowest, or the at least try to keep as shallow a tree as possible, right? So if we have multiple trees like this, if we wanted to join the tree DA with the tree EB, we would be joining, if both of them are the same rank, we would be joining one to the other, with the rank for the root node would then become one more than the total rank. If we had a two different trees, in this scenario D, then AE, then B, and in this scenario F, then C and G, and both of those have different ranks, we would always append the tree with the lower rank with the tree to the higher rank. That actually kept the rank of the tree as the maximum rank of the original set of two trees or pair of trees. So mainly we had two things. One was the make set, but that just did not take that much time. That was just creating individual trees for individual vertices. And then the main two things that we needed to figure out was the function that was find that given a particular node, tell me what the root node is. And that told us whether two particular nodes are in the same set or not. So let's say that we are trying to combine B and G. We then would need to figure out if B and G were in the same set or not. If B and G was in the same set, we would not combine them because they're already combined. Otherwise, we would combine them. So in order to figure out if both of those nodes are in the same set, we would need to basically ID them somehow as their set ID, and the set ID was the root node. In case of B, the root node is D. In case of G, the root node was F. And then we said that since the root nodes are different, we would basically combine them, right? Okay. And once we combine them, we get a new tree, and that was the main thing. But remember that the main bottleneck for our time complexity for combining these two operations, or basically figuring out if a particular node exists in a set, was that we needed to iterate through all the set of previous nodes or parent nodes. So for G, we needed to iterate through F, and from F, we need to iterate through D to get the actual parent node or grandparent node of G, right? The topmost root node. And that required log n time. And we said that we can somehow overlook or fix that by using a different data structure that basically said that instead of maintaining trees, we would still be maintaining trees, but we would maintain them in a different data structure that had a linked list sort of representation, where let's say that this particular node was um, where let's say that this particular node was to be connected to this particular node, then we would need to find the parent of all of those nodes. So apart from keeping the just recent parent, we would also be having a linked connection back to the root node, such that with one particular iteration, we would be able to find out what that particular root node was by just checking, by just having a link directly to the root node. And then we can say that, okay, I'm trying to connect these two nodes. I know that this particular node has a parent here, but the root node is this particular node that is big of one query. and this particular node has this particular root node, that is again a big O of 1 query, because we now would have links to the root node. And then basically our find operation becomes a big O1 operation. However, our union operation still remained a big O V operation, because we would still need to combine two particular trees into one particular larger tree, and that is still a big O V operation. But we can still sort of reduce the time complexity by just saying that we would always copy the smaller list to the larger list. That allows us to actually increase a bit more a bit more efficiency into this particular algorithm. Okay, so today we are going to potentially look at three more algorithms. Remember that we are discussing greedy algorithms. Kruskal's algorithm basically picked out random edges, in the sense that it is always going to pick out the smallest edge, uh, the edge with the smallest cost, and keep on building those trees. And finally, at the end of the day, it is going to have a singular tree that has the minimum spanning tree across the entire graph. Now that was one algorithm. However, that does require some bookkeeping to make sure that the algorithm works, right? We need to make sure that we know what the individual disjoint trees are at any point in the algorithm, and then we need to join them, and then we need to find the root node, and so on. Another algorithm that finds the least cost or the minimum cost spanning tree in a graph, and is a bit more simpler, is the Prim's algorithm, right? So it is a popular alternative to Kruskal's algorithm. And what it does is, so compare it with Kruskal's, where Kruskal would have picked random edges all the time and created those trees. Prim's basically maintains a current tree that we have explored so far, and only adds edges that are connecting to some undiscovered vertex, but it is exploring in an ever increasing fashion, where it is only going to look at edges that are connected to the currently explored tree. Right, so let's say that Prims has discovered this set of edges that has the minimum cost set of edges, and then it will only look at edges. Let's say that it has an edge here, it has an edge here, and it has this particular edge here. So it will only look at these three edges and choose the edge that has the minimum cost between these two set of vertices, that is the set of vertices that we have discovered and the set of vertices we have not discovered, right? So let's say that this particular edge E was the edge that had the minimum cost. So it picks that edge, and then essentially the set of edges, set of vertices that we have discovered starts from this point onwards and then grows towards this particular vertex as well. So the algorithm or the pseudocode behind Prim's algorithm is essentially, let's say that we do not have any edges so far. So we keep on repeating, and we pick a set S where there has no edges between S and V minus S, and let E be the minimum weight edge between these two set of vertices, the discovered set of vertices and the undiscovered set of vertices. And if E is the minimum most cost edge to our vertex where we have not discovered that particular vertex yet, we basically append that particular edge to our set of edges, and that is the new tree, and we keep on increasing our exploration distance as we move forward, right? Okay. So if we look at the entire pseudocode for this particular algorithm, we see that the input for this algorithm is a connected undirected graph with weights W and vertices V and edges E. And give me one sec, is the assumption that V minus S is already a tree then? No. V minus S is not a tree. V minus S is the set of vertices. So S is the set of vertices for which we have a tree here, right? V minus S is the set of vertices for which we do not have a tree. We are exploring towards V minus S. Yep, okay. So the input to Prim's algorithm is again a graph and its set of weights. And what it needs to return is the minimum spanning tree for that particular graph. So what it starts off doing is sets up all the cost to all vertices to 0, and then essentially picks a particular initial node, let's call that U0, sets that cost to 0, and creates a priority queue. Again, a priority queue, remember, is a queue that would have all the edges in some sorted order, or all the vertices in some sorted ascending order. Right, so essentially it picks the most weighted edge from this queue. If that particular vertex does not exist, then if we already have seen it before, then we compare the cost. If we have not seen it before, that cost is infinity, and we basically update it. So essentially this particular piece of code checks if we have found a more minimum cost to a particular vertex. If we have found a new cost that is lower, we essentially say that, okay, decrease the new cost and keep on doing it for all the edges that we have seen so far. Okay, so now
So that priority queue is going to have every single edge in the tree initially.
Yes.
Okay.
Yes. Yes, so that is what it does. It essentially has all the vertices, and it has the cost to reach all the vertices. Initially, all of those costs are going to be set to infinity, but as we discover more and more, and as we explore incrementally more and more, it would get updated costs. Okay. So imagine this algorithm a bit more clearly. So it starts off with a particular node, right? It starts off with some random particular node, called that U0, sets that cost to 0, and then looks at all the neighboring edges and picks the edge. Because we are using a priority queue, it picks the edge that has the minimum cost connected to that particular vertex, picks that edge, and then now it has two vertices. Now out of these two vertices, it again looks at all the adjacent edges, picks the edge that has the minimum most cost out of these two vertices, picks that edge. Now it has three vertices, and so on, right? So it keeps on incrementally growing its set of vertices. This gives us the benefit that we do not have to care about multiple different trees, because we are always maintaining a single tree. And since this is a greedy algorithm, it just picks the edge with the lowest cost every time and incrementally grows the tree until and unless it has seen all the vertices. So this particular idea that we are maintaining some tree and we are increasing this tree by just looking at these adjacent edges every time and picking the edge with the minimum cost. Does that algorithm ring a bell? Like, have we done this before? So if you think about it, this particular algorithm sort of looks like Dijkstra's algorithm, right?
Right.
Exactly. So this sort of looks like a Dijkstra's algorithm, where essentially we are picking the edge with the minimum most cost. We are not doing that in Dijkstra. There is a certain difference with that. Yeah, Dijkstra should be spelled as, I guess, Dijkstra. It might be wrong. Okay. So it picks the minimum most edge and then adds it to the list. So let's look at a runtime example for this particular algorithm. So let's say that we have this sort of graph here, and we want to find out the minimum spanning tree of this graph. So let's say that we start off at A, and then at that point onwards, we have the adjacent edges that go from A. We have A to C, A to D, and A to B. So we have the new costs. For B, we have 5, for C, we have 6, and for D, we have 4. We pick the edge with the minimum most cost, that is 4, and we now have the